Hey. G'day to another Toolbox Tech Talk. It's great to be back. So DJ Glen mate couldn't make it again today. He's been pretty slack lately, so he got the boss to come along and do this interview. And actually, I'm really enjoying these interviews. I get to learn heaps from my guests, and my guest today is someone that I'm sure I'm going to learn a lot from. It's Jeremy Tranter from ComAp. G'day, Jeremy.
Hey, Glenn. How are you?
I'm good. Jeremy, where are you coming from at the moment?
Mate, so I work remotely for ComAp. I live up in far north Queensland in the Atherton Tablelands behind Cairns, which I love. It's where I grew up. I got my own microgrid in the shed and electric vehicle in the driveway and cows out the window, so it's quite nice. And the joys of remote work and internet connectivity and all that sort of stuff, we can access most of our sites internationally. I was fault finding a site in Canada this morning, so it's great.
Wow. Living the dream. Yeah. So maybe just for our audience, tell us a bit about ComAp. Who are they?
Yeah, so ComAp has been in generator controls for over 30 years. We're a Czech company based in Prague, in the Czech Republic, in Europe. Roughly 600 employees worldwide. Australia's the largest subsidiary for ComAp, and we I suppose probably the most advanced in terms of system integration. But yeah, ComAp, you probably know, hopefully, from diesel generator controls, synchronous machines, and some of the solar guys probably know our protection relays, IntelliPro, Mains Pro, that sort of stuff. But yeah, we do power generation control, power management systems, energy management systems. So that's anything from a mine site, Pacific Island Nation, Prime Power, that sort of thing, to backup power for hospitals, data centers, that sort of stuff. And that's been our core business for, as I said, 30 years. Of course, microgrids, renewables, batteries has been on the radar for some time. ComAp Australia led ComAp internationally. We developed our Renewable Centre of Excellence 7 or 8 years ago now, I think. And that was sort of the start of our entry into hybrid microgrids. We developed a first hybrid controller that could do some PV stuff. A couple of years ago, we brought out our IntelliNeo range, which is solar, battery, wind controllers. And then more recently, hopefully we're going to talk about today, is our BESS controller, IntelliNeo 530. So we have this distributed architecture of choose the right controller for the right asset, and then you just bolt it on and they all talk together to share load and do power management stuff. So it's quite, I suppose, easier to use because we have pre-built applications, but there's customization as well, custom logic and that sort of stuff. So yeah, we're basically that on-site, real-time power generation control, secondary control layer, if people know that.
Right. So you mostly work in the sort of utility C&I space? Don't go down to the residential level?
Yeah, look, I mean, ComAp's solution has a certain cost, and it doesn't particularly scale with capacity, like size of your assets. It scales with the quantity of your assets, and it scales with the functionality that you need. So can we go and do a residential site? Absolutely. My whole farm here is running off a ComAp microcontroller. Works fine. But, from a cost efficiency point of view, it's a larger proportion of your capital spend at that smaller size. So we generally say we start to make more sense into, I say, a few hundred kilowatts, probably with multiple assets, mains connection, and then you've got solar and battery, and maybe there's a genset or something like that. But yes, definitely all the way up into tens of megawatts for large utility scale stuff in the off-grid space. Again, we don't really have a top side, but we are primarily around that sort of reciprocating genset control. And if you go beyond 50 something megawatts, you're probably not using diesel generators anymore. You're probably using gas turbines. And we do that sort of stuff, but yeah, it's sort of large C&I to medium utility is our sweet spot. Yeah.
Right. Well, full disclosure, I'm pretty new to ComAp and their controllers. I've been aware of them, but really never played with one or looked into it. But I know that they're highly regarded in the industry, and I can see what their role can be, particularly in things like microgrids. And that's what I'm very excited about too, learning more about that. So, to, to be honest, I hadn't quite realised that some larger inverters don't have any control system. All they do is just invert. And so we've actually got a Cinexcel 250 kVA unit here that arrived at the lab. And I didn't realise that you can't just program it to, self-consume solar and charge a battery. You actually need an energy management system. So that's what ComAp provide. It's one of their solutions.
Yeah, we do, absolutely. And you kind of picked up on a key tipping point in the industry, and guys coming through from the more residential end of the market are familiar with those, I call them EMS in the box solutions. You're familiar with the Sungros and the Victrons and the SMAs and the Selectronics of the world, Sigergy and all. There's a bunch of them now, but you're right. The control logic, the energy management logic to do what it wants to do, which is typically import, export, self-consumption, maybe some peak shaving, maybe some arbitrage on a residential application. Backup, of course, if you want that. That's all in the box, right, from those vendors. And for those applications in their architecture with their assets, it's amazing. Like, I'm definitely not saying don't put Selectronic in an application where it meets your needs, because it's a fantastic solution and it does exactly what you want. Where I don't believe there's really good solutions from vendors in the market is where you come up to that larger scale, where you want to have 50, 100 kilowatt machines, and you want to bring them in from different vendors, and you want them to do your custom site EMS stuff. There's not really a product that I've seen that does that, out of the box. And so you have to layer on this control layer, the energy management system, and that can be by your own PLC and program it. That's great if you know how to do it. Excellent. But what ComAp's solution is, and it has been, as I said, for 30 years with generators and mains connections and bus ties and all that, we've applied to the microgrid space, and we have pre-built firmware applications in our controllers. So to do things like import-export control, or control the battery to do peak shaving, or mains failure schemes, all of those functions, the sequences, the state machines, the control loops are all built into our firmware, and you can just choose the set points you want to make the application. And it's quite flexible to the point where you can make it do most EMS things within the out-of-the-box drop-down settings and things like that. But we also have PLC editor, so you can build your own logic and customize it and do all those sorts of things. So our advantage is that we generally, we are, generation source agnostic. We can take any diesel generator and control it. We can take any mains interface and control it, and similar with batteries and solar inverters, as long as they have the functionality on board that we need. Such as a way to control it, like Modbus Sunspec or something like that, and it has the core functionality that the end use case requires, then we layer that over the top and take control of it. So that Cinexcel example you gave, that's just a PCS. Straight up, there's no EMS on it. It has a start and a stop, and you can put it in PQ or VF or VSG mode, and you can send it PQ set points. That's it. It doesn't know anything that's outside of itself. So that's what we do. We bring all of the disparate pieces together and put them all together to make a functional power system, energy management system, and we try and do it in a way that makes it easier for you guys, for the system integrators, because it's complex. Power sharing, synchronizing, protection, those sort of things are complex, and we try and make it accessible to electricians and system integrators and those kind of people who are on the tools putting this stuff in.
I'm going to pull you up on a few things because whenever you mention an acronym, I like to help people understand what we're talking about because everyone's not
Sorry,
an engineer. That's all right. So you mentioned VF and PQ. What's that?
Yeah, so this is so we're talking specifically about an inverter now, or a PCS, power conversion system. Sorry, I'll just state that I tend to use the word inverter for solar and tend to use the word PCS for a battery, but they're the same thing, of course. So an inverter can operate or can be programmed to operate in a few different ways. The standard one that you'd be familiar with is the solar inverter, where there must be a live AC source, voltage and frequency on the bus, and when you connect the inverter to it, it's sensing that waveform, and it's not really a synchronization process, but it phase lock loops to the waveform, and it starts operating already in synchronism. That's part of the inverter startup sequence. And the inverter follows that waveform and injects current according to that. And that's called PQ mode, or real power, reactive power. That's where the PQ comes from. Or grid follow, or grid connected, or PWM, current injection mode. There's a whole bunch of ones, but basically you think about it as solar inverter, and it can't operate without an external source. Firstly, by definition, it has to follow an external source, and then also it's got active anti-islanding in there. So a BESS inverter or a BESS PCS can operate in that way. That's your standard residential SunGrows and Froniuses and whatnot that you're running in parallel with the grid. But a battery PCS that has a guaranteed DC source can also operate in what we call voltage source mode. And in this way, you can kind of consider it like a synchronous machine, like a diesel generator, where it just maintains a voltage and a frequency on its terminals, and it puts a 50 hertz sine wave, and it makes it exactly 240 volts or whatnot. And current flows by Ohm's law. You have an impedance on the network, and the inverter holds the voltage, and current flows. So that's two different ways of operating the inverter. If you want to have off-grid, and you want to be the battery to be the source, you must have a voltage source inverter. And so that's these two different modes of operation.
What about
VF, PQ?
VSG?
Yeah, that's an interesting one. So VSG stands for Virtual Synchronous Generator, and it's a terminology that has come with battery PCSs in this off-grid VF mode operation, voltage source operation. And there's a concept called droop, which is where you set a slope and the inverter is monitoring the frequency or the voltage on the bus. There's two loops, a frequency one and a voltage one. And if the frequency moves, the inverter senses it and it automatically adjusts its power output. Real power is associated with frequency, reactive power is associated with voltage. And there's no command coming from external EMS like ComAp or anything. The inverter does this itself, and it's dynamically following the voltage and frequency and injecting and absorbing power according to that. So that's droop. And then over the top of that is layered some synthetic control functions that are in the controller of the inverter to make it act like a synchronous machine. So there are things like inertia and delays and things like the way it responds, and it's basically to improve the stability of a battery inverter because it responds more like a diesel generator, which makes it able to share load with a diesel generator better.
That's really interesting. You often hear critics of renewables saying about they can't provide the same benefit that a generator can in terms of inertia. But are you saying they can with VSG?
Yeah, inertia is a tricky concept, and I must admit I'm not like the grid modeling power factory GPS kind of guy, so I probably stay a little bit clear of it. But inertia is definitely important to be able to cover that gap between when there's a load change, like say big load comes in or cloud comes over and the solar drops out, or you trip a circuit breaker on one of your machines. The time between when that event happens and when the secondary control can measure it, calculate it, and send a command back, that can be in the order of a few hundred milliseconds, 500 to 1,000 milliseconds, right? That's the time delay on a secondary loop. So the power system has to be stable for that period, a couple of hundred milliseconds, right? And power system time domain, that's a very long time. The power can be out for that before the secondary controller even knows. So you're trying to build this stability such that the system is stable even without any external control. But then the secondary controller comes in and says, oh, I want you to be actually stable over here, which is what we call isochronous control. We change the frequency back to 50 hertz. We change the voltage back to 400 hertz. And that's maintaining power quality. And it's also changing the way the units are sharing load. Like the battery might come in and take a big load first, but then you say, oh, I don't want to discharge my battery. Actually, that's what the solar's for, or that's what the generator's for. And you change the loading after those events. So this is to do with what we call primary stability and secondary control. It gets quite complex, so I'm not sure if I need to go further, but
No, that's really interesting. Is that related to FCAS service?
yeah, that's 100% exactly what FCAS is. So in an islanded off-grid power station, let's not talk about the NEM for a second. That's that process that I described. That's called isochronous control, where there's a load acceptance, everything follows by basic electrical law, and then some secondary controller comes in and says, no, I want you to be at a different position. That's exactly what AEMO is doing. They're dispatching every generator in the country every 5 minutes, and every generator is moving up and down. But 5 minutes is obviously far too long to manage frequency and voltage. And so that's what FCAS response is. So there's specific assets all around the country who are bidding in to say, if there's some big frequency excursion, something's happened, some big interconnector's tripped or a power station's gone or whatever, then these devices can come in automatically without having to be commanded, such that you get this sort of faster response before the secondary control comes in. So the NEM is operated like that, and it's orchestrated across the whole country, so it operates at a much slower speed. But it's effectively exactly the same thing, correct, but orchestrated across the entire East Coast.
Yeah, it's amazing. The biggest machine in the world, isn't it?
Exactly, yeah. It's when you think about the orchestration of how that has to work, it's a very complex machine, yeah.
Look, I can embarrass myself again. I was in a standards committee meeting with a bunch of network engineers one day some years ago, and I happened to lean over to one of them and saying, so with the grid, what's the right balance between generation and load? And he kind of looked at me slightly dumbfounded and said, exactly the same, Glenn.
But they have to be exactly the same, otherwise things don't go very well. Yeah, and so most of the generators, like the coal generators and those guys, in the big generators in the grid would probably be performing some kind of droop response or frequency support as a part of their connection, because they're so big they have to be participating in that. And then if I've got a battery connected in my factory and it's a 1 megawatt FCAS participant and I'm going through some aggregator, then my battery will come in and give the local network 1 megawatt. But the idea is that the whole FCAS system across the network is trying to assist that big gas turbine just because it's taken a long time to speed up or slow down. That's inertia.
Yeah, indeed. I better obey my own rules too. I mentioned FCAS, frequency control and ancillary services.
Frequency control, ancillary services, yeah. So this is it's a market. It's similar to part of the electricity market, if you're familiar with the wholesale spot price in the NEM. That's what we're just talking about in terms of dispatch. But there's also a pricing market mechanism through FCAS, and it's basically you say, I'm going to be available and I have to be ready. And if you don't dispatch when there was a frequency event and you were dispatched, then you get fined. But if you do get called and you do dispatch correctly, then you get a payment for providing that service, which is proportional to the power that you generate, not to do with the energy, because it's a very short duration event.
Yeah, I sort of got interested in this when we acquired these 3 250 kVA Cynic cells and 2 megawatt hours of batteries.
Yeah.
And we've got a 1.5 megawatt high voltage connection on the property that's totally unused. It's sitting in a paddock.
Wow.
And it's got 16 homes on the other end of it. So basically it's unloaded and very clean. I'm told that's a good thing. It doesn't have a lot of noise on it. So there was a company interested in doing some trials with their software. Hasn't gone forward yet, but it's in the back of my mind. But anyway, let's do a bit of a segue onto the IntelliNeo system. So it can do all of the things we just talked about, right?
Yeah, pretty much. So I just want to loop back to ComAp's control architecture, which I mentioned is a distributed architecture, which probably maybe not well understood as a general industry concept, because you may be more familiar with a centralized architecture where there's like one PLC, one controller brain, and it's talking to the generator, and it's talking to the battery and the PV, and it's gathering all that information and it's processing it all, and it's commanding all of those assets individually. So ComAp doesn't do that. We have the distributed architecture where every asset has its own controller. If you have one generator, you put a controller on it. If you have 2 generators, you put another controller on the second one. A battery has a battery controller. PV has a PV controller. Mains has a mains controller, etc. And all of these controllers talk to each other on a shared communications bus, and they all publish everything about what they're doing, and they subscribe to all the information about all the other controllers are doing, and then they make their own decisions about how they need to participate in the power system. So that provides a lot of flexibility in terms of modularity of your system. Just put one controller on now because it's PV mains. Want to add a battery later, another controller, then add a generator. That's fine. It does make the control logic to load share slightly more complex, but that's our job. You don't have to see any of that. That's all in our firmware. So what the Neo 530 controller is a BESS package unit controller. And I want you to think about that in the same way as a generator package unit controller. So you'd be familiar going by a genset, and it's got an alternator in it, and it's got a diesel engine, and you have to be able to control the speed of the engine for frequency, and you have to control the excitation of the AVR for voltage, and you've got fuel and crank and cooling and all that stuff, right? So that's what our generator controllers do. We've built that for a BESS. So you take a PCS like your Cynic cell, you take your battery system with your BMS, say Pylon Tech or BYD or something like that, whatever you like, and you put it in a box, container, aircon, transformer, insulation monitoring, all the extra stuff, and you bring that into the ComAp controller, and it integrates that whole system into a single battery power generation unit that's ready to parallel and synchronize and load share and participate in an energy management system with an AC connection, just like a generator. And so you can now, packages, for example, or packages who are building BESS packages, maybe locally, maybe overseas. You can put this on and sell it ready to go. And it, as I said, it's flexible to be programmed. Or if you're wanting to integrate your own, as you just described, you've got some PCSs and you want to build your own, then we can help you, or your system integrator can help you to build that together and make a package that does your thing. So the Neo 530 knows battery things. It can handle DC bus. It can handle pre-charge. It can handle all of those things we just discussed in terms of PCS operation. So we have voltage source, fixed voltage source operation, which is like what a Selectronic or a Sunny Island would do. There's no frequency control, voltage control. We can do PQ mode operation, solar inverter, grid-connected battery, and we can do VF droop or VSG operation, which is our preferred mode for off-grid because we can parallel with generators, synchronize, load share, and you've got maximum capability. But that...
What about that VSG, by the way? Does that also mean you can sort of control generically other inverters that use frequency power response mode?
That's exactly how we control inverters in an off-grid scenario. The disadvantage of those EMS in a box devices that we mentioned is that they don't have any external control provisions because they weren't designed to do that, right? So there's no way to parallel a Selectronic with another Selectronic or with a Sunny Island, or unless you have the proprietary communications between them to do the synchronizing and the load sharing. ComAp takes that away, and we basically do that VSG control. So it gets quite complex, I suppose. I don't know if we want to cover it here, but it does allow us to parallel a voltage source inverter with another voltage source inverter or another synchronous generator or another infinite bus like the mains, because we have the ability to change its voltage and frequency reference in the same way that we do with a generator. And therefore we can synchronize it, we can load share it, we can parallel it, we can make it participate in an energy management system. And so that gets some really nice functionality.
It must be controlling a contactor to decide when the power is actually paralleled, not just
monitoring. So we do a standard what ComAp calls a forward synchronization process, or if you're familiar with the standard generator synchronization process, if the bus is already live and then you start the generator, then the generator is going to be live on its incomer, but the circuit breaker is open. We have voltage measurement on the generator side, we have voltage measurement on the bus side, and then we control that generator to synchronously, and then we close the circuit breaker perfectly in sync. We do the same thing with the battery.
Yeah. It's a lovely thing to watch on a dual channel oscilloscope, watching the two waveforms line up and then on a 0 volt crossing join together.
Yep. And on all our screens we have the synchroscopes and stuff like that, so that's quite fun to watch. And obviously tuning synchronization is something we do all the time, because you don't want it to be something that's violent or going to cause disturbances as you close breakers and things like that. That's part of what we do. But yeah, I think that's something that I'm not sure is well understood out there, this concept that it is possible to parallel a voltage source VSG inverter with another voltage source. That's what we do all the time. You don't have to put the battery in PQ mode just to parallel it with a genset. In fact, we prefer not to, because you lose a lot of functionality and a lot of system strength. But
wow, I hadn't realized that was even possible. Yeah, that is really interesting. Hey, Jeremy, maybe I'll just kind of compare how I've managed things here, which is I'm effectively the IntelliNeo on my microgrid. And it's a very clunky approach. As you probably know, it's been a bit of a growing thing. It was I call it the accidental microgrid. It did just start off with one SP Pro, and it became 3-phase with 3, then it became a power chain with 6.
Nice.
And we kept on adding more and more solar inverters and hybrid inverters to that grid forming system. So the Electronic SP Pro is the VF grid forming source, and that's still the case. But we then have the problem of how much can it control by using frequency shift. So the SP Pro can do VSG, but only at a certain rate. So you have to be able to protect it from reverse power. At one point, we had a 4-to-1 ratio, so 4 times as much renewables on the output of the SP Pro system than the SP Pro was rated for. Now, that's a pretty dangerous kind of situation, but fortunately, they were mostly Modbus controlled Select Sun inverters, and Modbus gives very fine-grained control. But I've now got loads more systems. We've got a 800 kilowatt-hour battery system, 50 kilowatt PCS connected on in PQ mode, hanging off this. So it's all kind of manual. Like I actually adjust the settings almost every day to keep everything in balance. But what you're saying, that something like IntelliNeo as part of a suite of controllers does that innately, inherently.
It's like it's up to the customer what their use cases and requirements are, of course, but certainly the intention is that it's fully automated, hands off, and it should look after itself. Now, of course, you can't solve all problems with control systems. There is a part of primary asset sizing and capacity that's important. Like if you don't have enough solar to charge your battery, then your battery will just sit flat and you'll be running on generator forever, and our control system can't get you out of that. but certainly the use case and the functionality and all the control loops to do that all fully automated. Even Black Start itself, again, if it has an outage and things like that, that's all standard for us. Yeah.
Yeah, so one of the problems I have is the sunny day problem. So the grid forming system gets up to 100% storage capacity, so it's full. So it wants to curtail generation, and it can do it to some extent with frequency, but occasionally you'll get so-called cloud edge effect. It's overcast, the sun pops out, all the solar, we've got like about 150, 200 kilowatts of solar out there on the microgrid, all comes on at once. And the SP Pro goes, help, I'm just going to kick them all off, go up to 55 hertz and kick everybody off. So we then have a deficit suddenly, and suddenly all the load falls back onto the grid forming system, and we get a big reverse kind of discharge happening. And so it causes a bit of a voltage and frequency move around. It's not elegant. So I'm really interested that you can actually parallel two voltage sources together and maintain that stability or with VSG functionality.
Yeah. So, that's out of the box. And I mean, you've just, I suppose, exposed your non-conforming electronic design, but we do similar things. Like we have a solution where we can use a synchronizing diesel generator, like one of our synchronizing controllers, and we actually parallel it to the SP Pro on the AC1 on the load port, so that we actually control the charging or the dispatch of the generator and the charging of the battery. In that case, we have to read out the limits of the PCS, this electronic, and make sure that we don't reverse power it, because if we're reverse powering it, it's just going to trip itself on its own protections in the same way. So we don't want to do that. But yeah, if you have the ability to change that voltage and frequency reference on a generator or a voltage source, VSG, BESS, then you have the ability to load share, and the other device doesn't actually need to know. So we do that. There's clever ways to do a few of those things. I did just want to pick up on the cloudburst topic, because that's something that that's hurt us over the years, in the early years, because our solar control just used to be a closed loop PID, if we know PID, proportional integral derivative control, which is basically closed loop, so it's always chasing the target. And what happens in a solar inverter is, because it's a non-guaranteed source, if the sun goes away, it obviously can't generate, but our control keeps winding up. I want more solar, there's not enough solar, until your set point gets to 100%. And then it comes out from behind the cloud with 1,400 kilowatts per square meter, and smashes your system, and you have a huge event that's not what you want. So we have actually built, I suppose, anti-integral wind-up or anti-cloudburst algorithms in our solar control, so that the set point that the PV receives is maximum offset from what it's actually doing. So the set point goes up, and if the PV doesn't come up, then the set point doesn't go up anymore. And only when the PV comes up does the set point go up. So it can't have that huge blast, because if the solar's only doing 20%, the set point's probably 22, 25. So when the sun comes back, it can only go to 25, and then we keep bringing it in a controlled way.
Yeah, okay. That's really interesting.
Concepts that people in Grid Connect probably don't ever think about, because you've got this infinite bus, and if you export a bit, no biggie, but in an off-grid, the lights go out when you do that.
I'm going to start calling the grid the infinite bus. It sounds so cool.
Infinite bus, that's what it is. Solves a lot of problems in power systems, I'll tell you that.
Now, I probably should have started with this, but your devices are basically like small packaged units which communicate via Modbus, Ethernet, etc. Is that correct?
Yeah, so our intercontroller comms that I talked about, the sharing between all the distributed controllers, we're actually using CAN bus. So we have a CAN bus network. It's because we come from diesel generators and industrial engine control. CAN bus is J1939 and the SAE automotive CAN is where that came from. And also when we're talking to diesel engines, most diesel engines have an ECU and an engine control unit on it now, and we don't actually directly control the fuel. We command the engine control unit. So it's all CAN bus based because it's vehicle and engine background. Certainly in PV and battery world, it's Modbus, and like SunSpec is hopefully becoming, a little bit more of a standard. Chinese don't seem to align to it just yet, but generally the European guys are pretty good on SunSpec, and we've got good interfaces for SunSpec. But yeah, it doesn't, as long as it can be controlled, like we could have low level analog loops or some other protocol converter if it's needed. But yeah, definitely Modbus SunSpec makes life easy. Yeah.
So I'm putting my installer hat on here and just thinking about how this has worked in practice. So you physically associate one of your controllers with an asset. You are running comms cables between assets in daisy chain.
Yeah, so the CAN bus is a daisy chain serial. Yes, yep. Oh, we have other options. We can extend over fiber optic and things like that. But yeah, if it's under 200 meters, then we can go copper.
And what about over TCP IP connections?
Yeah, so if we're talking TCP/IP Modbus to the solar inverter or the battery PCS or some energy meter or something, then yeah, that's only limited by your Ethernet network. So, and if you want ComAp to support you with system integration, we can do all of that. Design your control network, to current cybersecurity standards and all that, or we can sell you the box and you can come and do some of our training, and you can go and do it yourself. Depends on.
Wow. Well, I'm just thinking how it would work here on my crazy microgrid, having like 20 different systems, mostly small residential systems, but a few large ones. All of those would need their own controllers?
Yes and no. So we want to be able to dispatch each primary generation asset to perform its key function. Now, in your microgrid, I suppose I probably don't know it too well, but let's say you put a Neo 530 on the SynXL, the big BESS, and you've got that as your primary source, and you wanted to parallel some other solar, just PQ connected solar, and maybe you had some PQ residential batteries that you wanted to take control through ComAp. Like I have a SunGrow in my shed that I don't use the SunGrow EMS. It's all by external Modbus control. It works perfect. So you can totally do that. If it's a PQ inverter that doesn't need to do synchronization and we don't have that voltage frequency reference control, then we can just do it by comms, because a solar inverter, you just send it a command and say, turn on and do this power. A PQ battery can do the same thing. So that could just be
using
done by
SunSpec
Ethernet.
compliant inverters or using the DRM functionality?
Preferably by Modbus. Yeah,
Yep.
It could be SunSpec, or SunGrow doesn't comply with SunSpec, but they have a published Modbus list. As long as you can get access to it, it's programmable in the controller. You don't have to get us to program that interface. You can do that yourself. It's custom interface development.
So how do you turn off the built-in EMS in a
in a SunGrow? There's a setting which I'd have to look at the Modbus list, but it's something called external EMS control, and you set a parameter and it starts listening to the Modbus control. And so instead of you've got the SunGrow meter on your main incomer and it's talking to the PV inverter on the backup bus and all that via its own proprietary serial or Ethernet comms, I've just turned all of that off and I'm commanding the SunGrow PV inverter directly and the SunGrow hybrid inverter directly, and commanding.
Isn't there a kind of concern there from the manufacturer about trust of that you can't harm their equipment if you're controlling it?
Yeah, that's 100% a valid question. That's a really good question. So one of the core functionalities inside the Neo 530 and also our other Neo controllers for that do BESS supervision is this concept, what we call dynamic operating envelope, which is we want to read out all of the limitation or the operating envelope limitations from all of the subsystems. Primarily that's the battery, and we read the BMS to say what's the max charge current, what's the max discharge current, do I have a voltage condition or a temperature condition or some unbalanced condition that it's reporting to us to say you need to derate. Usually it gives us an analog number in in amps or kilowatts that we must respect. And we put that into our firmware, and when we do the control logic to send the power command to the PCS, it's restricted, it's clamped by that operating envelope. So let's say the power requirement was more than what the BMS could do based on the load sharing EMS algorithm. That particular unit controller would say, no, I can't request more than that from the PCS because the battery won't like it. And if you were to do that, then either the BMS should self-protect itself if it's a good one, and it'll just trip itself, open the DC contactor, and everything lets go. Or if it doesn't protect itself, then you're going to do some damage. And so that's a core part of what we do with every battery integration. If we're doing it, we want that what's the warranty, what's the performance requirements, what's the operating requirements of this BMS, of this PCS, or whatever that you need, so that when we program it, that it doesn't. We don't want to be responsible for damaging your battery. Absolutely not. And that's a core part of the functionality.
What about damaging the grid? So do you also control the grid profile?
So we have mains controller to be able to handle that grid connection part. Again, it's distributed architecture, so we have a controller that understands a connection between your site, the microgrid, and the infinite bus, right? Mains is an uncontrolled infinite bus. You can't control it, of course. We're way too small. So it's whatever its frequency is, whatever its voltage is, you must modulate your site to achieve export or import or whatever you're trying to do. So our mains controller measures the mains, and then we send commands out into the fleet that sits inside the site to achieve the functionality, right? So let's say we want to do zero export, ramp up the PV until the mains controller says you're doing zero, then back it off.
So this would be your IntelliPro, Mains Pro?
No, the IntelliPro and Mains Pros are just a protection relay. So all they do is detect the grid excursion events that the DNSPs are looking for, and to say, anti-islanding or power quality issues, and then you must disconnect. So there's no analog control or EMS functions in those two devices. The mains controller function, the mains controller product is called IntelliMains. So we have an IntelliMains 210, a 510, and a 1010, depending on the versions.
Ah, I see. Right. What about auxiliary systems? Can you also interface with those? HVAC, fire detection, etc.
Yeah. So again, if it's associated with that unit, that generation unit. So if it was a generator, we're controlling radiator fans, or we're controlling fuel tank fill, or all sorts of things like that. Door access, e-stop, all that stuff. Transformer monitoring, if you're connecting through a transformer, all those sorts of things. In a BESS, HVAC's definitely a key one. Lithium batteries commonly have some kind of active cooling. Insulation monitoring device, if you're aware of that, it's common to have the DC bus floating, not referenced to Earth. And so you want to have an insulation monitoring device that's measuring resistance to Earth and looking for that first fault scenario. Access control, door switches, emergency stop circuits, transformers, whatever you need, we can bring those in, and we have the ability to add custom protections and alarms and functionality. You could say,
is the coffee machine up to temperature? Yeah.
And say, we need to do some derating because one of the HVAC units has failed, or something like that.
What about smart loads? Can you control some loads like water heating and stuff?
Absolutely. Yeah. So in terms of standard firmware functions, we have load shedding and load reconnection just as a standard function, because that's come from power stations since forever. So, if there's under frequency event or we've run out of spinning reserve, we can start to shed loads, and then they can automatically reconnect. Other things like smart load banks. We've done dynamic load bank control where we didn't have good control of PV, for example, and we had to turn on some load bank to stop the power station reverse bus. But it's basically the ability to dynamically modulate load based on solar curtailment. Solar is currently curtailed, and battery's full, so let's turn on some load. So EV chargers or hot water systems or HVAC. Like that's easy. It just comes down to the interface. Like we don't have OCPP on board our controller, but certainly we could get a command out of our controller that could feed through an OCPP client to control an EV charger.
So through an API, like you're using the cloud as the interface.
Well, either locally with a direct gateway on site or through a cloud API. That's all possible, yeah. We have our web supervisor platform, which connects our controllers on site to our own cloud by our own proprietary edge-to-cloud link, which we call AirGate, which is an encrypted, cyber-secure channel. And then that goes up into our web supervisor platform, which is fleet management, like iSolar Cloud or SolarWeb or Sunport or whatever. You can see all of your assets. You can control them, turn them on and off, and change some of their settings and things like that. There's some basic trending and alarms. But off the back of Web Supervisor, there's also a REST API. So if you want to connect your cloud, your smart dispatch, your VPP, your DERMS, even your ERP system or some corporate dashboard that you've got, you can just connect to our REST API and grab that data. Or we do spot price dispatch through it, or VPP dispatch direct. Ready to go.
I think you just broke the internet with TLAs there, 3-letter acronyms.
Sorry.
But anyway, I'll let those ones slide. I think those who need to know will know.
What I mean is remote dispatch from the cloud, direct to ComAp controllers at the edge. All you need to do is to connect to our API in the cloud. You don't need any other assets. Or you can put your own edge device on the edge and connect to our devices directly via Modbus or hardwired I/O. We've done both for VPP and virtual power plant and F-gas frequency control solutions. So,
what I found very useful as our microgrid has grown is having loads that respond to surplus renewables. So as any curtailment starts to occur, we'll see frequency rise. And so we've used products like Catch Power's Catch Control, my PV, their hot water controllers, and that means we can have a dampening effect on that curtailment. So we're not wasting the energy, and we're also not having a big swing in terms of voltage or frequency. It works really well. But there's one missing part, which is more and more we're adding heat pumps, and heat pumps aren't easy to control, though many of them have compliance to a EU standard called Smart Grid Ready. Is that something you're familiar with?
I must admit I'm not familiar with Smart Grid Ready. Is that like a remote dispatch protocol similar to, say, IEEE 2030?
Well, I'm about one tiny step ahead of you. I just know that it can be used to control heat pumps as opposed to switch them on and off. There must be a ramping that goes on, like telling them to slow down. I
suppose if it's a heat pump, same as an air conditioner, if it's inverter type, variable speed drive, then you can control them with some kind of analog control rather than on off. Obviously each unit will have minimum turn down and all sorts of things that it has to do to actually function. I'm sure it has to have a minimum speed to pump the refrigerant around. But it's not uncommon to be able to have some high level, say, Modbus interface to an air conditioning HVAC system or a heat pump or an EV charger, where it's analog control where you can say 0 to 100, or maybe it's 40 to 100 or something. It's minimum turn down, but that sort of control is definitely super handy for those devices that can do it. Block loads like hot water systems, you probably need some kind of smarter device that's got some kind of PWM thing in it, like what I suppose Catch Power are doing, to be able to control the load in an analog way. But again, if anything that has a control interface and can be commanded to do the function that you want, we can build that into our EMS.
Right. So, Jeremy, I did reach out to you a while back when I was involved in helping design a grid-tied microgrid for a small town here in Victoria. And we came up against a whole bunch of problems, which you guys pointed out that you could actually solve by control. We had the infinite bus, i.e. the grid, we had like 130 homes and 30 so businesses that all would needed to be islandable in case loss of that beautiful infinite bus, which apparently happens when there's storms. Also, a backup generator that can be used when there's not enough renewables. Multi-site renewables, both on homes but also some on businesses, larger systems, and spread over a DNSP's network and not all in one location. So I think that distributed model that you have was about the only way we could find a solution to this control system.
Yeah. Yeah, look, distributed control, as I said, has a lot of advantages in the modularity of it. And again, as I mentioned, the complexity comes in how you build those algorithms such that you can split them all out. Now, that's what we've done. So it's sort of easier for our customers, and I hope that they agree. So yeah, it's about putting the right control solutions in the right places, and then it's about comms. Like your point about frequency shift control is a key one, right? SMAs, electronic, been doing frequency shift control for quite some time, and we also do it. Like we have the ability to change the frequency of our generators and our batteries in the network to control PV out in the network. It's common in Pacific Islands because putting fiber optic 20 k's up the island, it's just not in the budget. It works well as long as you've got inverters that do have a good frequency droop roll-off response. AS4777 current, latest couple of versions, usually pretty good. But again, it's not something that is standard if you're not using an AS4777 inverter, perhaps. The issue with that one is that power quality. Is it okay for your network to be running at 51 hertz all afternoon and 49.8 hertz all night? Many places that's totally fine, no big deal. But I will tell you that one of our customers, one of the big DNSPs in Australia, still, as of this week, requires ComAp to do frequency error correction management in our power stations to manage the drift of clocks. So we have an algorithm in our controllers that calculates the error away from 50 hertz as an integral, and then modulates the frequency to make sure that 24-hour clock drift is 0. So
I've got a funny story about that clock droop problem. You probably know this one, but I was at a workshop run by SMA maybe 15 years ago, and it's when Sunny Boys were the hottest thing you could buy. And they said, we have something new. It's called Sunny Time Machine. And we went, oh my God, what? What technology is this? And they basically explained that when there's frequency shift occurring on an off-grid installation, you'll get your clocks running fast during the day. So they have exactly the same number of cycles in reverse, less cycles to make up for it. So your clock is accurate over 24 hours. It's accurate.
Over 24 hours, it's accurate. But if you look at it in the afternoon, it'll be fast. And if you look at it in the morning, it'll be slow. So if that's a problem for you, then frequency shift is maybe not the right solution. And high-level comms certainly can do it, but you have to have communications, whether that's running a fiber optic or you want to do a point-to-point wireless link, or there's mesh networks and private 5G available now. But comms, some way to control your assets is generally required.
I found one more problem with frequency shift. As the frequency goes up, of course, any motor will run a little bit faster. And my coffee machine will go a little bit faster, and so the shots aren't as good,
good
in the afternoon.
Makes a difference. Yeah, right.
But and I've even heard that some appliances spit the dummy. So it is a clunky way of controlling assets.
You can have issues. Like we've got one example, I suppose, of one of our early customers who was using the Neo 530. They're a genset and now a battery packager. And so they hire gensets out to construction sites all the time. And they had a construction site where there was some underground drilling, I think, and the variable speed drive that was running the drill was tripping out all the time because they had two 500 kVA gensets And every time the machine would start, big load, and then the frequency would sag, and then the VSD would trip because the frequency sagged. So that customer put 2 of those 500 kilowatt Cell inverters inside of his BESS packages with Neo. So we had 2 ComAp 500 kilowatt gensets and 2 ComAp 500 kilowatt batteries on site, and the site ran solid for 8 weeks without a problem. And it was just on cycle charge. 2 batteries ran the thing for a while, and then when it got flat, gensets turned on, or when the load increased above a certain limit, then the genset turned on. And construction site ran flawlessly for, I think it was 8 weeks or something. After the first 2 or 3 weeks, they couldn't even drill.
Yeah. Wow. That's big dollars lost.
VSG and fast frequency support.
That's pretty impressive.
That's quite a nice outcome for that customer, because I think the construction site was pretty stressed in the early days.
Hey, Jeremy, I just noticed we've sort of come to the top of the hour, and I think I got through 10% of the questions I had for you. This has been so fascinating, and I've already learnt heaps that I was hoping to learn. But maybe you can just give us a bit of a wrap in terms of ComAp services and how people might reach out to you.
Yeah, for sure. So ComAp, we can sell what we call white box. So you can come and buy the loose controllers from us, and you can take that away and build it into your own system. You're the system integrator, or you choose your own system integrator. If you want to get involved in understanding more about how to do that yourself, we do training all the time. We have training courses across the country. We've done 34 training sessions this year and trained over 200 people. And that includes single genset, non-paralleling stuff. If you just want like a basic 2-wire remote start genset for your standard Selectronic, or if you want to learn about paralleling, we do parallel generator courses. We've got the BESS 530 training that we've just started doing this year, so you can come and learn about how to integrate your own BESS. We have 8x5 support based in Australia here, and I'm not 100% sure whether it's ready. It's definitely coming soon. We're going to 24/5 support internationally, following the sun. Wow. As well as we have our own engineering and system integration, full turnkey control solution services here. So you can come to us and we can design the system, functional description, do all the drawings, build you a control panel, not just the controller. We'll build the whole panel for you, test it here, ship it to you on site. Your electrician or your electrical contractor installs it. We turn up, we test it, we commission it, we make it work, we hand it over, we give you training, all the documentation that goes with, so you can get that service. Or you can start with one and move to the other, right? We can take you on the journey, and we do one with you, and then you kind of go on. So we're happy to train people. We want more people using ComAp, however that works for your business. Get in touch with us. All our contact details online, and with sales team across the country. We're going to be at All Energy in October, so come and see us at the stand. We have a microgrid test lab in our Brisbane office, where we have a 50 kilowatt SunGrow battery and a 30 kilowatt Cell package that we've integrated ourselves. PV on the roof, diesel gen, load bank, mains paralleled, all permitted to do grid parallel and all that. So welcome to come and have a look if you want to see it in action. You can do that remotely via Teams, or you can come and see us. And we're always interested in understanding like what your use cases are, right? Like if you've got some use case that maybe our firmware doesn't already meet, then we're definitely interested in understanding that and building that in and understanding what your needs are. So even if you've got something, reach out, and we'll let you know if we can do it, or certainly take it on board and put it in the R&D list.
Well, thank you, Jeremy. I might actually send you my crazy SLD of our microgrid just for you to have a chuckle at. See if you can suggest some improvements. It's been great talking to you. I really genuinely have learnt heaps, and probably get you back sometime to go through the other 90% of the questions.
Oh man, I'd love to. If people are interested, I mean, I'll talk about this stuff all day. Like, I love it, right? Like, it's
now, I will put
fun.
some links in the description that people can click on to go to your website, etc. So they'll be able to reach out to you. But anyway, I think I'll just do the wrap. And so thank you very much, Jeremy. I'll put you in the weight room and we'll have a chat afterwards.
Thanks, Glenn.
Okay. Well, yeah, that was a pretty special Toolbox Tech Talk for me, particularly, talking to someone way above my pay grade, but also about some amazing products and the features they offer. So for me, the takeaway, number one thing, I hadn't realized it's possible to actually have multiple voltage sources synchronized and in a mode that's quite useful for microgrids. So I kind of want to learn more about that Droop functionality. So anyway, thanks for watching another Toolbox Tech Talk. Maybe DJ Glen may next week. I'll try and encourage him. He's been a bit shy lately to turn up and do his thing. Certainly, when there's something in the industry that's happening, some new bit of standards or issues, he likes to kind of have a word about that. So we'll see what happens. So till next Sunday, 1 o'clock Australian Eastern Standard Time. I'll see you all then. Okay, check it.